Hey everyone, thanks for coming to the RS seminar. Our guest today, I'm extremely happy to introduce Professor Chung from Caltech. He's a professor of both aerospace and control and dynamical systems there, and there's also a senior scientist at JPL down the road. It's a great pleasure for me to introduce Sunjo. He's sort of one of the bright stars of my little corner of robotics, dealing with space systems in particular, and really looking forward to the talk. Also, Sunjo is a recipient of numerous awards, including the NSF CAREER and AFOSR Young Investigator and Caltech Best Paper Awards that I will not bore you with coming. So thank you to Sunjo for being here, and we're really looking forward to the talk. Oh, and one note for those on Zoom, we're not monitoring the chat, so if you want to ask a question, just unmute and speak up, especially later during the Q&A. All right, thanks everyone.
Thank you so much. Thank you so much, Zach, for inviting me, and it's great to be here. So I'm going to share some of my recent research with my students. It's going to be more like an overview, but I'm going to show you a bunch of new videos. So hopefully you enjoy them. Some of my prior work, and I'm going to mention those. But before we talk about our own robots, some successes in the field are basically deep learning. And you see that, I mean, you heard a lot of news about the AlphaGo beating human Go champion, right? And then recently, actually, they kind of did a success in the like a board game, Stratigo, right? And it's called the Deep Dash. And you can see that this kind of work actually is based on some very structured environment with a finite discretized work. But our robots actually work in continuous state and action space. And you have to deal with the continuous dynamics. So I'm going to talk a lot about dynamics of the robots. And then in unknown environment, right? It's not like just like a grid world, right? So I think there is a kind of a still disconnect between what you can do with a machine learning and what you can do with a real dynamical system, dynamical robots. So that's what we are going to focus on today. And before I talk about the my robots, how about this? And I'm honored to be here in Robotics Institute of CMU. But you have to agree with me, robots are not just walking robots or manipulators and so on. Spacecraft, in my opinion, are robots. And aircraft increasingly becoming autonomous, and they are robots. And in particular, spacecraft, once you launch a spacecraft to Mars, and there is a time delay of 5 minutes to 20 minutes based on the location of your Mars. And that's real justification of having more autonomy in spacecraft, right? So I'm also working with the JPL to really increase the autonomy of our spacecraft. So clearly, spacecraft and aircraft or drones are robots, okay? And they move fast and extreme environments. So what kind of extreme environments I'm thinking about? So my former student, Guanya Shi, will soon join RI, Robotics Institute, as a faculty. And this is Guanya's work with a micro-connect, and obviously some Reuters TV video. And obviously Michael is having so much difficulty in holding the umbrella. So that's the kind of like a mild gale type of wind. It's like 44 kilometers per hour. And we have a drone that can actually fight that kind of wind. And it's called the neural fly, machine learning based flight controller. And next to it, we have demonstrated, actually no machine learning. We demonstrated kind of perching maneuver using kind of bird-like robot. It's a bird-like robot because you can actually move the left and right wing, like almost like a flapping independently. So that way you can control the orientation of it. And then you can actually do a pinpoint guidance. And actually you can land and perch that glider robot on a human hand. And another example is actually, it's not showing here. We have another video based on my prior work on swarm dynamics. I actually work on swarm robots and swarm spacecraft, and we actually studied the flocking dynamics of birds and reverse engineer that. And this is the first ever demonstration of a herding live flock of live birds, basically doing herding algorithm, right? And these are examples of fast speed robots. And if that's not fast enough, I'm going to mention this another project for the neural rendezvous, and we actually just submitted a paper And I'm not going to go into the detail of that, but essentially we developed the machine learning based approximation of some real-time model predictive control. So that way you have a very resource limited hardware on spacecraft because you don't really need, you really need a radiation hardening for your spacecraft. So you don't probably have very fast computation. The idea is that when you have a once in a lifetime or once in a civilization kind of opportunity of doing a long debut or flyby maneuver with an interstellar object like this, you need to have some very robust method that can actually deal with a huge uncertainty because we don't know where these objects are coming from. So this is the one example of using a neural network-based method or machine learning-based method. That is essentially you kind of approximate the real-time need for real-time computation optimization using neural network approximation. Of course, that's much easier said than done. So you have to guarantee the stability and so on. And this is basically experimental validation we have in the lab. So we have a spacecraft lab. It's kind of floating on the flat floor. It has spacecraft-like actuators, thrusters, and reaction gears. And basically, we are demonstrating neural long debut machine learning-based planning algorithm so that it can actually go into the target, the comet shape, and then stop there very accurate fashion in the presence of a huge uncertainty. So I'm originally coming from control community. So there is a kind of a mismatch or bridge, the gap between control theory and the machine learning. So as I said earlier, there are two main applications of machine learning for robotic application, in my opinion. Number one, it can actually deal with some uncertainties, like non-nominal scenarios, like certain failures, wind disturbance that you didn't take into account in your modeling stage. So you can use a machine learning-based method to improve that. Or as I said, you have a large computation you have to run some model predictive control online that you can maybe approximate that using neural network functional evaluation. That's maybe an advantage. But the thing is, you have to make sure that there is a safety, robustness, and stability guarantee, right? So that's actually where control theory is going to be helpful. So we just recently offered a tutorial session in CDC on this topic using contraction theory. It's called the contraction theory for learning-based control, and we recently published the tutorial paper in our annual reviews in control. So hopefully you can check that out. So briefly, I'm going to talk about that Leonardo robot as one example of using control theory to achieve something new in a robotics capability. And I'm going to emphasize a lot about this like a layered kind of a hierarchical design of a control system, learning-based system. It's not going to have just end-to-end learning that's going to solve all the problems.
One question about the rendezvous project. So over there, what is the goal? Like, is that object flying? Is like some asteroid coming over and hit that through some?
Yeah, right. So you want to minimize the distance between the final trajectory of the spacecraft and then interstellar object. It's almost like you have maybe intercepting a certain object using drone, but you have a huge uncertainty because you don't know where it's coming from. But you once you get closer, like within 500 kilometers, 1,000 kilometers, you can actually use an onboard camera to do relative navigation. So you can, as you approach the target, you can actually reduce the uncertainty. So we are doing a onboard planning and control based on that information. And then I'm going to talk about some of the stability tools that can be used to kind of guarantee provide some analytical or theoretical guarantees when you do some machine learning based control. So I'm going to talk about that and some of the recent work that is attempting to approximate some of the onboard computation, because now everyone is doing kind of a optimization based something like the MPC and sequential complex programming. So I'm going to show you some examples of using machine learning, and with the emphasis on the stability guarantees. And then eventually I'm going to talk about basically tracking control using machine learning. So this is the kind of main message for safety critical system. I talked about the high-speed spacecraft and drones dealing with a huge uncertainty like unknown wind, because it's kind of independent of your state. You have to deal with it. And there are, I mean, this is a typical block diagram. My point here is that just you have whatever like desired maneuvers and characteristics of your robot, and that's your command, and then that's the output. You are not going to replace all the blocks using single machine learning block. my point is that you need to have multiple hierarchically combined system. It's just common thing. And you might actually apply some machine learning to motion planning problem, but you have to still guarantee stability and so on. So we have some approach of doing that. So now, Leonardo robot. I have not used any machine learning something, but this was the first robot that bridged the gap between aerial locomotion, basically flying, and the walking bipedal robot. And the idea is simple, right? Basically, you add the propellers so they can actually stabilize the walking motion, and so you can occasionally fly. And motivation of this one is that I hear a lot about the quadruped, and this is very impressive.
Go over loose rubbling terrain
bipedal
and
robots
be able
cannot do
to
that.
traverse
Robots
where you
cannot
need
do
it to
that.
traverse.
It has native obstacle avoidance.
Quadruped can do that easily.
Back up again. It can.
But why do you bother? Look at our Leonardo robot. We start walking and find the stair, and I want to traverse that stair and then boom, just fly over your obstacle. So that's the idea. And take a look, certain posture, orientation of the leg and the whole body. You have to somehow synchronize these leg joints with the propellers. We have 4 propellers to stabilize the motion, perfect. And also it allows the Leo robot to fly.
One question about.
This is a robot that walks, flies, skateboards, and slacklines. But why? This is a robot that
this
walks,
is a drone with
flies,
so obviously it's going to affect any
and
flying vehicle. Right? So this one doesn't have any payload right now other than
this is a robot that walks, flies,
so you can actually walk and fly,
skateboards,
and then you can do also
slacklines.
skateboarding. It's the first bipedal robot that actually can ride a skateboard, but obviously it's not pure bipedal robot because we are using propellers. But it's just showing the multimodal capability, locomotion capability of Leonardo robot, and also, most importantly, slacklining. It's like an embodied pendulum.
This is
you
a
can walk on
robot
the
that
same
walks,
cable,
flies,
but stabilizing it. And then briefly, I want to say that this is the first probably bipedal robot that has high heels. And obviously it was a kind of a design for like a walking system, but eventually you can power down the motors so you can actually have it stand still without wasting any battery. So that was one purpose. You can see that once it stops walking, power down, and then stand there. So it has some small design innovation, but obviously highlight of this maneuver, challenging maneuver it can perform is actually slacklining, right? And it's a famous Veritasium video. We got the Veritasium crew actually filming this robot. Even under this wide bouncing of a thin wire, it's clearly walking because the wire is supporting the weight. And we can show that the beauty of control system, right? We have a hierarchical control system. I said I'm going to mention a lot about hierarchical control system. There's nothing new about hierarchical control system. Everyone used that, right? For example, spacecraft, you have a reaction here, you have a low-level motor control, all the way to a higher-level attitude control, and even some planning. Something like that. We have a separate walking and then flying controller, kind of seemingly integrated, but running at different frequencies, right? So obviously, ancestor of Leo, where we got the motivation. Of course, we cannot forget the Buzz Lightyear. But for joking aside, we look at we are Iron Man. And then when you look at this Iron Man, and actually you have this like micro turbine engines strapped on the legs and the arms. When this British inventor, Richard Browning, lands, he's carefully synchronized and control the limb motion so they can actually control the thrust vectoring. We do something like that using Leonardo, using synchronized control. So speaking of a synchronized control, we can actually look at the biological systems. And then it's a very complex system. Then when you talk about the biological central nervous system, we always talk about brains, for example, like basal ganglia is kind of responsible for kind of reinforcement learning or supervised learning and so on. But the thing is that our human central nervous system is a very, very crude machine in terms of time delay. So how you can actually deal with this kind of time delay, because we have a very crude muscle system and so on. Everyone knows this. It's a central nervous system is composed of brain that can actually command high level kind of command over your motors and muscles. and spinal cord that has a basically local loop that can actually deal with this kind of a delay. So that's the key idea, hierarchical stabilization. And how you're going to achieve that using the robot. So one idea example drawn from my prior work is that I actually worked on central pattern generator based limit cycle control. So I actually apply that to the flapping flight. So basically the idea is that instead of commanding all these different joints of the flapping flight, the best to have more than 36 joints on their wings. Instead of trying to command all these different oscillatory commands, you have a central pattern generator that can generate these rhythms, and then you can actually synchronize them. And then instead of controlling individual signals, you can actually control the phase difference between different limit cycles. And limit cycles, we use the Hopf oscillators that are representing the basically patterns, like a limit cycle patterns, rotations of your flapping flight. And this is finally our attempt to demonstrate what's the kind of motivation and what we can do with this flapping flight. So this is that famous backbot I worked on with Professor Seth Hutchinson when I was in Illinois. So again, I'm going to go into each block's motion planning and tracking control to kind of talk about some application of machine learning based method to, number one, maybe reduce the computational intensity of some of the kind of optimization based method. And number two, maybe to deal with some very challenging unknown environments or models like a wind-based disturbance. So again, I mean, this is a conventional reinforcement learning problem. In fact, what I'm doing using some more conventional optimal control method can be viewed as a reinforcement learning, but essentially the original form of the reinforcement learning is basically, I said optimal control, essentially dynamic learning. Optimization with the time steps. Typically that involves the dynamics, right? But reinforcement learning typically doesn't assume that you know the dynamics. You don't have a model. This is essentially a model-free version of dynamic learning. So my hunch is that I'm going to talk about our physics-infused machine learning-based control method. So basically, you should not ignore your knowledge about the dynamics. You have to make use of it and try to identify what you don't really know and try to focus on that and apply the maybe machine learning method. So speaking of that, we are going to start with a motion planning problem. And oftentimes you can formulate this as a optimal control problem. And if you have a finite horizon, that's an MPC. You keep updating it, that's an MPC. But you have to deal with the nonlinear dynamics. And this is a spacecraft example. And reconfiguring multiple spacecraft into the desired shape. And oftentimes you don't give the terminal point. Terminal point is not determined. And you have to deal with the inequality constraint, and some of them are non-convex, like a collision avoidance. So this is a pretty well-known method. We have a series of the steps to convexify the method, because nobody can solve the exact optimal control solution to that original problem. But you are doing series of approximation, like decentralizing cost function and convexifying the non-convex collision avoidance constraint by drawing hyperplanes. But then you are also doing successive linearization. I think this is still better than just one-time linearization, because you are doing kind of iterative sequential convex programming so that you can further improve the linearization. We published this work, first applying that to multi-agent coordination dealing with highly nonlinear dynamics. And this is a very popular these days. But we combine that in the International Journal of Robotics research paper. We combine that with a high-level planning. What is that? Basically, I give the command. 4 robots, green robots, from whatever initial condition, why don't you make this particular shape? In this, for example, 4 rectangular shape. So I don't specify robot 1 goes to this point, robot 2 goes to that point. It automatically figures that out using kind of some target assignment algorithm or terminal polynomial algorithm. We have used the Hungarian method before, but in this paper, we are using the distributed option by Professor Brasikas, and that's inherently kind of distributed. So we're kind of having these 2 loops like simultaneously running, and this can be viewed as another hierarchical loop, running some decision-making slow loop, and then you have a trajectory optimization faster loop, and even feedback control is going to be even faster. So you have to make sure when you have these multiple loops kind of combined and then running some sophisticated system, you have to make sure that a combination of these different loops and time scales actually leads to still stable convergent system. Yes.
So with the target assignment, what is the objective? Why should one target be preferred over another target?
Because I mean, we are kind of optimizing over certain cost function, maybe that could be integral cost of your energy, like or like if it's a spacecraft, like a fuel cost, right? Energy cost. And so if you have like 1,000 agents, you want to make some complex structure like a Taj Mahal, you don't really assign each agent because it depends on your initial condition and whatever individual constraint, like a vehicle constraints and so on. So what they do is that, why don't you make a Taj Mahal shape? And it's going to figure out what's my best location at the terminal time. That's what it's going to figure out automatically. And that's one example about making a decision at a higher level, because you have to find that point only at one time step, that's terminal time step. Whereas you have a trajectory optimization means that whatever discretization you have to find that for each control input and X. So if you take X and U trajectories and you take a U and apply that to actual hardware, then it's more like a conventional MPC. My approach is that I'd rather just compute the desired X, and then you still do a feedback control to guarantee the stability, because you still don't know that that model you have used is correct or not. Still, there might be some errors. So I talked about fast loop and slow loop. Another thing I want to mention is that, yes, if you remember from the reinforcement learning, pure learning, basically you can actually talk about Bellman and principle of optimality. So it's a conventional problem. If you are solving continuous dynamics, continuous state, optimal control problem, you can use the Hamilton-Jacobi-Bellman equation. Or if you have some constraint optimization, you can use the country again. My approach is that this is a very brute force way of doing it. It's called a direct transcription. Basically, you turn the optimal control problem with the optimization problem. You're doing discretization of your time and successive sequential convex programming. I think that's way you can actually really solve the problem. It's not optimal. It's still suboptimal. It's all about finding a better suboptimal solution. But if you are doing an HGB and you want to solve the numerically partial differential equation, how are you going to handle these inequality constraints like collision avoidance? When you, especially when you have like a multiple agents interacting and changing, it's going to be very difficult to solve. So my preferred way of doing it is that maybe still it's going to be suboptimal. Still, it's better to solve that problem, optimizing something cost, making sure it's not colliding with each other, because it's actually satisfying the collision avoidance. I'm going to show you how you do that under presence of stochastic noise. Further extending that, obviously my dream is that obviously building something like a microcontroller, and your department has a strong connection to this movie, but essentially typical microboard
can now be accomplished by one person.
Command. Why don't you make this kind of shape, and it can automatically figure out the location of that desired location, doing a collision avoidance maneuver and maybe trajectory optimization
anywhere.
So that's kind of part of my research. Swarm control. And then we running that previous algorithm of the sequential convex programming with combined with the distributed action algorithm called the SATO. I give a desired command, why don't you make a UIUC, and then you can automatically kind of configure that. And then if it's hit, if maybe it's a swarms of spacecraft is hit by asteroid like this, you lose certain agents, and then you can redistribute them using this simultaneous optimization using a SATO algorithm. It can actually do that. And obviously we are demonstrating that using autonomous docking on our spacecraft simulator facility. And eventually, I don't command the spacecraft one goes there. I just make a command. Why don't you make an upside down T shape? And you can automatically figure out the optimal collision free path and makes the collision, which is docking, only at the terminal time step. So that's kind of implementation of this algorithm. But this is a prior work, they basically published in 2014 and 16. What's the new extension? What if you have a stochastic uncertainty, right? I don't know why it's starting that. It's automatically stacking. Well, okay, talk about that. So what if your dynamics are stochastic in the sense that it's a non-linear, but you have a stochastic noise? It's actually for the stochastic differential equation. I don't know why it's actually starting automatically. Maybe I'm going to speed up. So one idea is that I'm going back to this. Now we replace the dynamics with the nonlinear dynamics perturbed by noise. And number two, you're in inequality constraint, because that's a challenge. Like one problem of the HJB approach is that, yes, you can actually maybe deal with the equality constraint, like you want to go to that target and you can modify the cost function. But how you want to deal with the inequality constraint, like a collision avoidance and input constraint and so on. And so that's what you are dealing with. You can easily deal with it, although we are doing kind of a suboptimal approximation. But we are dealing with a multi-agent system, which is very complex. But in addition, we have this probability of certain constraint should be greater than 1 epsilon, where epsilon is kind of a risk measure. So this is called the chance constraints. It's basically probabilistic. So idea is that you have a certain way of converting that stochastic differential equation to the deterministic differential equation, and you have to modify the chance constraints as well. Again, what we are doing here, we are doing multi-agent, including single agent, trajectory optimization, but in presence of uncertainties, both in the dynamics and also chance constraints. One preferred way of doing this, we just published this in the Transcription robotics, is that we actually took the generalized polynomial chaos approach. So it's almost like if you are familiar with the structural dynamics and FEM, it's almost like a Galerkin projection. So you can actually have this coefficient xi, j, for this homopolynomial equation, and the z is the random variable, because it's a normal distribution with a zero mean and then unit variance. And we can actually turn that into basically dynamics, deterministic dynamics of xij, and the error between those two, SDE, stochastic, and deterministic, will be zero as you increase the number of the polynomials to infinity, of course. And then you can now it becomes a deterministic problem. And one example scenario is that, okay, I have multiple agents. You have to avoid a collision. And then compared to this kind of a non-stochastic version of algorithm, you can smooth it. We can kind of figure out, okay, in the presence of uncertainty in the object collision avoidance location, including the neighbor's location, we can kind of see that boxes have shifted a little bit. We can find like a safe probabilistically safe path. So that's another way of extending this numerical solution to the trajectory optimal control problem. And it's going to be very difficult to solve that problem using conventional reinforcement learning. Going back to this diagram, I don't know, it's kind of why it's just changing the slide automatically, but I'm going to move on to the now machine learning based approximation of this like sequential convex programming that's solving trajectory optimization of many agents. And one example is glass. And actually, I'm very proud of this work. I don't know how well known this work. And it got this honorable mention best paper award from IEEE. So idea is that actually, let me show the video. We are approximating this centralized optimal solution using neural network, but neural network is local. You only know imperfect partial information because you want to implement this algorithm and you only know the basically neighbor's location only, and or maybe whatever neighbors you are communicating with. So basically, idea is that you have this permutation invariant neural network. Why permutation invariant? Because if you stack the neighbors, you don't really care neighbor one, neighbor two, because they are same neighbors. So you have to have this permutation invariance, so invariancy. So that's actually deep set. And of course, we have some safety, kind of essentially like a feedback control loop to really avoid a collision in addition to the neural network approximation. So what it does, it basically approximates the decentralized optimal control solution for past planning problem. You can reconfigure them to the desired location. And that's one. So we published this work. So what's the advantage of this? You are sending a spacecraft. You don't have a radiation hardened computer. You don't have a fast computer you can run. Then the advantage of this method is that you can actually avoid or eliminate any onboard computation and replace that with a neural network function evaluation. That's maybe a small contribution you can think about. Another extension is that, okay, maybe still you cannot solve the very complex problem like a differential game, like maybe 3 agents kind of competing with each other. And then we kind of look at the AlphaGo and AlphaZero. But as I said earlier, AlphaGo and AlphaZero is on the structured, discretized action space, action and also state space. Obviously, everything we know about in dynamics, spacecraft, rockets, aircraft, Leonardo robots, bipedal robots are continuous dynamics. So basically, we found a way to apply this Monte Carlo tree search for like a decision making. And you can build this as a kind of reinforcement learning problem. And there is a centralized agent, then there are updating policy network and value network. So it's kind of similar to the alpha 1, alpha 0. The difference is that we have also learner, smaller Monte Carlo tree search that's based on imperfect partial information, because this is a multi-agent. You only know the neighbor's location, for example, right? So then that's maybe much more efficient, and you do multiple iteration like using simulation based on Monte Carlo tree search expansion, and that's called the neural expansion. And instead of biasing the pre-node selection using the policy or value network, like in the case of AlphaGo and AlphaZero, we are actually using a neural network to output the actual control action. So that's a slight difference. So that's a nice extension of this multi-agent coordination using neural network. And this is experimental results. And obviously, 3 red agents kind of competing with the 3 other neighbors to actually go into the target area. So now we talked about motion planning, and then I'm going to talk about some feedback control problem. But before I do that, I want to find some mathematical tools that guarantee some stability or robustness in this motion planning and control method using machine learning. So this is a kind of a contraction theory. It's actually a way to find the incremental stability. So if you learn nonlinear control, you are probably familiar with the Lyapunov function. The difference between Lyapunov function and this contraction theory, which is a means to compute the incremental stability analysis, is that instead of finding some, like a scalar function, basically maybe some total energy or kinetic energy, and then you show that Lyapunov function is converging to 0, instead of doing that, we basically have some, like a volume constructed out of your dynamics, if that volume is contracting over time. That's why it's actually contraction theory. Then you can say that your dynamical system with your preferred closed loop control is contracting with a global and exponential stability, which means that now you have a disturbance, and you can kind of analyze the kind of input state stability or bounded input, bounded output stability. Another benefit of doing incremental stability is that basically when you have a hierarchically combined system like this, I don't know how you do that using conventional way of doing passivity. So it's very easy to understand. You can see that from this kind of space system, but now with a virtual displacement vector delta. So what is the delta? Oh, I'm supposed to remove that. I forgot to remove. Oh, good. So you have an original dynamics closed loop. X is non-autonomous. You have a dependency on both state and t, and it's very straightforward. I mean, it kind of resembles some nonlinear, like a Ricardo equation of some sort. But you can see that you can actually construct your differential dynamics of your virtual vector displacement vector delta x. That's infinitesimal delta. You can easily find in the calculus of variation if you are doing optimal control theory. So if delta x going to 0, then the distance between any trajectories from the single dynamics, because you can start from any different initial conditions. But no matter what, regardless of those initial conditions, all these different solution trajectories will converge to single trajectory. That's very beneficial because a lot of that system you're dealing with is not about stability about a point. Although you can convert the maybe error state vector, and you show that error is converting to 0. Same thing as tracking something. These are the trajectory with a tracking error 0. But here you have one trajectory and second trajectory. You want to converge it. You have to have them converge to each other. So that's the incremental stability theory about multiple trajectories. And that's very useful for our learning-based system or robot system, because everything is trajectory, not a point. So taking an example of a machine learning system, we just published this annual reviews in control paper as a tutorial paper. It's actually quite straightforward. You have original dynamics, that's true, but you don't know about that. And you approximate that with a learned model, and there might be some error, like this. So the difference between true dynamics and then learned dynamics is the error. And you can view this as a kind of disturbance, which means that you are using the same analysis for bounded disturbance, bounded in the sense of L infinity norm, or you can also do that to L2, or any norm. So under that disturbance D, which can be viewed as a learning error, and you can actually bound that this is now global exponential convergence. Important thing is that exponential convergence. A lot of people in the linear control theory, we also sometimes use asymptotic convergence and so on. I think we should only look at the exponential convergence because they can guarantee the actual rate of convergence. You can characterize it. And furthermore, once you have a bounded disturbance like D right there, you can actually use a comparison lemma to actually compute the exponentially bounding disturbance. So that's, you can compute that mathematically, and we are making full use of it. And once you have that learning-based error, you can kind of update that if you have more information, and you can keep reducing your learning error, and that's what's happening. So what if you have a now stochastic noise? Same thing. This is a conventionally for estimation problem. We do a lot of estimation problem for machine learning system. You have a stochastically perturbed trajectory, and you have an original trajectory not perturbed, or maybe perturbed by another stochastic noise. And they are going to incrementally converge to each other, but not perfectly to zero. They are going to converge to each other in a mean squared error. So if you have original dynamics without noise, they are converging to each other for deterministic stability. Now, under stochastic noise, they are going to converge to each other in a mean squared error sense. Okay, and then you can apply that and develop some controller and an estimator that can actually bound the error between desired trajectory and then your actual trajectory. For estimation problem, you can reduce the error in an exponential fashion between your estimated trajectory and your true unknown trajectory, and that's an estimation problem.
Question.
Yes.
So here W, does that represent the control?
Where is the W?
The meter process.
Oh no, that's a noise. Noise. Yeah. So with G, X, T is assumed to have control input there. So you are using, once you design a controller, how you can actually prove the stability, and you can use the information to design a controller. So that's what I'm talking about next year. So I don't actually design a controller. Once you have a controller, this is actually called a CV stand controller. It's almost a kind of non-linear analog of H infinity controller. You can actually guarantee the robustness, and then you can actually still, you see the similar bound desired error between XD and minus X mean squared error set. It's going to be bounded, and you can take that cost function. So as T goes to infinity, that's going to be the upper bound. You can actually try to minimize that in real time, and that's how you design a controller. And you have something like a LMI associated with it, a Ricardo equation associated with it, and then you can actually convexify the problem. You can solve this problem as a convex optimization. The problem is that you have to solve it every instant point. That's the problem. So we have a kind of approximation of that using neural network. So that's another kind of approximate, value of using neural network for machine learning control system. Finding the almost like a stability certificate, like a Lyapunov function using neural network. So now let's switch gears because we talked about the stability theory. Now let's switch gears to talk about the tracking control block of your system, layered system. So typically you have dynamics, and then again, I think one message is that oftentimes we can try to run everything. So you don't know anything about the drone dynamics, which is not true. You know a lot of them. And so X can be written as X dot equals F of X comma U, and then focus and identify what you don't know. And that's maybe, in this case, wind-based disturbance or some additional disturbance you don't know. So that's where we actually focusing on. So there are neural lander family. We started with a neural lander where you actually improve the landing performance. because you have a kind of reflection of your air is called the ground effect. And you can kind of counteract that disturbance using neural network approximation. But this is based on offline learning, combined with the feedback control. We kind of extended that to neural swarm, where you can actually counteract the aerodynamic interaction using swarms. So that's actually Guanya Shi's PhD work with some other PhD students. Finally, we presented the, now, okay, we talked about offline training. How can you adapt this deep neural network used to represent that unknown model like G of X, U, T? And how can you adapt that or retrain that in a real time? So we have some partial solutions there. So that's kind of neural fly method. Speaking of neural lander, it's offline control, but big contribution out of this work is that there is a technique called the spectral normalization. It's a big black box. And the problem is that it's not interpretable and you don't know what's going on. So even if you did your best to minimize and isolate what machine learning is responsible for, in this case, predicting the XYZ disturbance force and XYZ torque, disturbance torque, when the drone approaches the ground. Basically, we train the neural network, but you do a spectral normalization. Basically, you can actually bound the slope of the neural network when you do training using this singular value or Lipschitz constant of your network. And so that, once you know that, of course, we know how to stabilize the system with a bounded Lipschitz constant. So you can actually design the exponentially converging controller that, as I talked about, using contraction theory, and we can prove that you can find the gain lambda sufficiently large so they can basically override the whatever Lipschitz constant you have out of your neural net. So that's one contribution. And then you can have a better tracking performance of smooth landing, because previously existing ground effect model from the aerospace community was only function of distance, scalar distance. Now this neural network is a function of XYZ vector, and also it's a function of a velocity. You can have a different ground effect as a function of velocity. It clearly outperforms conventional PID control. And it can do something like this. It can track. It can go over the table. So one example benefit of spectral normalization is that you can go outside your training domain. That's typically the problem of any neural network-based method. You can see that when you do a spectral normalization, when you go outside your training domain, you have a continuity in terms of a response. So more predictable. So if you don't have a spectral normalization, you just can't jump randomly, which is not really reliable. I don't want to use this method. So that's like the right-hand column. So obviously, spectral normalization has this kind of regularization, like a smooth property that ensure this kind of performance. And obviously, for this kind of table problem, all of a sudden, once you go over the table, you are experiencing the aerodynamic disturbance. And you can see that with the spectral normalization, you can kind of better predict the table shape. And that's one example of why spectral normalization is working better. So again, I think what I'm trying to convey here is that if you wanted to do a completely end-to-end learning of this neural lander, like a drone landing in the presence of a ground effect disturbance, probably it's going to take a lot of time and probably without guaranteed stability. So this is a more principled way of doing machine learning-based control, in my opinion. And we kind of apply that to the swarm interaction, because you are talking about ground effect, like air blowing each other. You can actually destabilize your swarms of drones where they are flying in close proximity. So we have this heterogeneous set of drones. It's actually crazy flyers, and this is kind of a record of how closely they are flying, because we are using neural swarm to counteract or cancel the aerodynamic interaction between the agents. And furthermore, in this paper, we actually use that learned model and then recompute the desired trajectory, because your optimal control method or MPC method is optimal with respect to your model you are using, dynamics. If the dynamics are wrong, your method is suboptimal or even not safe. So we keep updating your MPC dynamics or model in equality condition using this learned model.
The drone's like aware of
Yes, yeah, in this case, we kind of command that they are using only local computation. That's on the way of showing the deep set. So you're only doing local interaction, but obviously we are not focusing on sensing problems. So we give the location of the neighbors.
Same with the table. With,
Yes, yes, right, yes. But that one we are using the motion capture system. Yes. Of course, there are internal IMU system and so on. So what is the finally neural fly? Okay, this is also kind of a flying training method. And then, for example, if you thinking about the wind-based disturbance, like you are flying an airplane, sometimes you have turbines, and that's completely independent of your speed, your location, right? It's really coming out of nowhere. So you have a constant, you have a suddenly disturbance, not just function of U, but also function of certain T or W, like this. So that's a neural fly. There's a need for online adaptation. But think about this. Although we talk about very efficient, like a deep neural network with a spectral normalization, still we wouldn't be able to kind of do a whole back propagation and retrain the neural network. There's no point of doing that. By the way, you still have not collected enough new data to justify retraining of a neural network. And even if you have that, I mean, there's not going to be effective to do all this back propagation, retrain the neural network online. So I think we found a kind of big compromise in adapting or rapidly adapting the deep neural network. That's a neural fly. So what is it? I'm going to skip the video. So basically, we are using adaptive control. Adaptive control is known to, basically, you have some parameter kind of uncertainty, you can adapt that. So key idea is that you are using adaptive control as a kind of way to rapidly adapt certain part of neural network. What is that? You have a multi-layer deep neural network. Last layer, if you can actually do some mathematical manipulation, you can actually see that your last layer coefficient, whatever weights you have in the last layer, can be a linear function of this form, where A is not a function of your state, it's a function of some wind-based parameter that you don't know. It's state independent. It's not function of your state, like velocity and position and orientation of your spacecraft, aircraft. So this is a neural fly. You have a meta learning method that can kind of really precondition your deep neural network so that last layer can be adapted using neural network fast and efficiently. And then you combine them. So this is the way to train the neural network. We have an adversarial cost function here, which means that you make sure that you do a conventional least squares to better approximate your wind-based disturbance, but making sure that your last layer is independent of your state. And whatever wind-based disturbance is only captured in the A. And that's what we are updating in real time. So we are not doing a full real time retraining of a whole neural network, but this method makes sense because you train the neural network so that your A last layer weight is very sensitive to whatever time varying disturbance. That's wind. And then this is a little bit of a contraction theory and adaptive control. So we are doing composite adaptation. It's originally popularized by my former PhD advisor, Chung, but we actually rediscovered that because you have a conventional tracking error-based adaptive control, right? That's being used for this community, but also it has some a least scarce almost Kalman-Fitter based approach. So you actually combine them, and the idea is that how you prove the stability. So this is a kind of conventional problem. You have a very nice hierarchical kind of combination there, and you can actually basically prove the stability under certain assumptions like bounded certain errors and so on. And then you can actually find what parameters you have to tune. So this is a more interpretable way of looking at machine learning based control. This doesn't solve every single problem. If you apply that to single different dynamics like quadruped dynamics, it's not going to work. You have to maybe retune and readjust how adaptive control works in conjunction with your neural network based approximation of something. So that's the final result of a neural fly compared to the other state-of-the-art tracking control method. It kind of reduces the tracking error of this following some agile trajectory in the presence of time-varying winds even. And we are blowing the wind up to 44 kilometers per hour. And this is a comparison with some of the other tracking control methods using, including aeronautic control. And you can see that even if we slightly change the model of the drone that's different from your trained model, it still outperforms the existing control method. And again, we trained the neural network only up to the 6.6 meters per second. So we eventually, when you do a testing, we actually blow the wind much higher speed, at least twice fast. So now I talked about the stability, but now let's switch gears as a final chapter of your our proposed method of using or leveraging machine learning control. I talked about proving the stability. So you find the reaction function. If you're using contraction theory, that's kind of limited to finding this M metric function. So because in a contraction theory, your reaction function is always quadratic function of delta x, the virtual displacement. What is the delta x again? That's infinitesimal displacement. And you integrate that, it's almost like Tesla length integral. So the trajectories, the distance between multiple solution trajectories of your nonlinear dynamics, potentially stochastically nonlinear dynamic, can be converging to each other, single trajectory, right? So now finding the reaction function is all boils down to finding this positive Riemannian metric, positive matrix M, or inverse of that W. So we found a nice way of kind of doing that using neural network, because typically you will see lots of papers finding reaction function. So there is an existing method called the sum of squares, right? But this actually worked better than sum of squares because it can handle higher dimensional system. And then we are using, again, spectral normalization, otherwise it's not going to work. So this is the importance of a spectral normalization. You regularize your neural network whenever you do a training so that you can actually have a bounded slope of your neural network. So what is this? Again, we are using neural network approximation of a reaction stability function when you design your controller. So again, you sample the multiple trajectories and you have a computed optimal like a positive definite function that's used for contraction theory. And then you train the neural network. And then you can use that for control design, motion planning that we are talking about, and still is better. It's outperforming other conventional model predictive control and or conventional nonlinear control in terms of handling this disturbance. And also furthermore, it still guarantees certain stability under certain assumptions of a bounded disturbance. So, all right, so in conclusion, when you apply the machine learning for robot dynamics and control, I think my preferred way of doing that is not to do end-to-end learning. And because you have to deal with the dynamics, and let's face the fact, you are in the Robotics Institute, you know a lot of the dynamics of the robots. And again, please include the spacecraft and aircraft in your robot. And whether it's a walking robot or spacecraft, yes, there is no flexibility, it's a rigid body dynamics. And then question is that what you don't know, and there you cannot maybe consider applying machine learning like we did for neural fly to estimate the wind-based disturbance, and it was quite effective. In my opinion, it's not going to be easy. You should completely replace that with a reinforcement. Number two, I think we still found a good use of a machine learning-based method. And when I say machine learning, very narrow scope, basically using a deep neural network to approximate some numerically optimized solutions, including stability, like a reaction function for like a positive Riemannian metric, or I can say that reaction function, or some optimal trajectory. And you can approximate that using neural network with some stability guarantees. And actually, it worked fairly well in kind of approximating the actual solution so that you don't have to run expensive computation. Number two, I think machine learning can be eventually very useful to handle some of the off-nominal scenarios. So I talked about disturbance, like wind-based disturbance, that you don't know anything about it. So maybe it's a good idea to try to approximate that using machine learning method. But there are some other challenges like failures. You could have a random failures of the wings and propellers, and that's certainly we are looking at those. And those are good kind of examples where machine learning based method can be useful to really achieve the full autonomy and more adaptation. And then we also presented some safe motion planning algorithm using uncertainties and so on. And then all these methods actually kind of developed under this assumption that we can actually look at the convergence and certain stability properties with some bounded assumptions using contraction theory. And then I think key thing about the contraction theory is that basically you only look at the exponential convergence. You don't compromise with the asymptotic convergence, right? So then we can kind of mathematically guarantee certain exponential convergence in terms of a converging bound, error bound, even with the machine learning method. So that's something that we've been looking at in our research group. So again, I think in closing, I think all these different pieces of the system, whether it's a motion planning, learning-based tracking control, state estimation that can be done using some machine learning-based method, especially if you're using computer vision. Those blocks can be combined with the assumption that we can analyze this stability of this each building blocks, and you can ensure that combination of these different blocks can still lead to stability or convergence or guaranteed robustness of combined systems. So that's actually the approach I've been taking with my students and my research group members. So thank you so much for listening to my talk. And if you have any questions.
Curious, what assumptions do you have to take to do this spectral normalization? Are there certain characteristics of the neural network that you have to design in order to apply to any?
I think you can apply to any neural network. We use the ReLU because it's actually easier to compute because it's just like a matrix W and then you just check the singular values. Yeah. But I think you can certainly use the other neural networks. Yeah. Yes.
Just a quick question. So when you do the contraction method, you put contraction in the system, you are not proving the existence of caveats. You have to make the caveat.
So this is a good question. So we don't really, yes, because we actually use the convex optimization that CV stamp. So we actually is a control over. So you have to have some controllability assumption and so on. So you actually always can find the M, and then you are actually using the power of X and M to train the neural network. So I think maybe one thing that I can offer to you is that if you find a reapproach function can be any nonlinear function, right? But in our case, it's always quadratic function, but not with respect to state, but delta x. So you can always find the M as long as you can find the stabilizing conditions. Yes.
So on slide 15, where you were comparing your algorithm with the L1 adaptive and AB method.
Yeah.
So I noticed that the tracking error decreased with increase in the speed of the wind for one of those.
No, yeah, that's not our results. So that's their results. Ours is keep increasing, but still better than their method.
Yeah, I was just curious if you have any thoughts on why would tracking error decrease with increased disturbance?
I think it has to do with the kind of it has a low pass filter, and then by the way, I think we use the same computer, but typically their method in their published paper is a lot faster computation. We are only updating at 50 Hz, the control input, so it's much slower. Still, kind of it worked very well. To answer your question, I have to maybe, do you know how to actually go back to? I have to do this. Yeah. So our main result is actually, I think, blue, and this purple is still better than other method. Is actually kind of transfer learning stuff. So different drone with the original neural network.
That's starting the baseline and the AD.
I don't know exactly why that happened, but still, like the error was pretty large. Right? Yeah. Oh, yeah, exactly.
Take one if no one else wants to. So I'm curious, the sort of learning the contraction metric stuff. If you thought about, connections between this sort of thing and like actor critic methods where you learn a value function approximation, connections between obviously, like the value functions or the up and out functions, and if you thought about these and kind of things and the connections to what the more maybe traditional RL community is doing.
Maybe because I mean, when you actually prove the convergence of certain kind of quadratic function, you can view that as actually like a cost or reward function. And obviously, oftentimes in machine learning community and other control community, we actually obsessed with our LQR cost function, like a quadratic cost function of a state and quadratic cost function of a U. And essentially, this is kind of proving the convergence of that cost exponentially, maybe exponentially something like a too stringent for that kind of problem, because as what you need to do have is just like a decreasing cost. One thing I can think about is that there is a kind of inverse optimal control theory where in the case of adaptive control, the conventional adaptive control, you can always find the corresponding quadratic like LQR like a cost function that's actually will have that adaptive control as a solution of your adaptive control. So maybe that's one connection where stability theory is somehow connected to some cost function that can be minimized. Maybe that.
So one other thing along these lines, the methods, you still have to compute like a geodesic under that metric, right, online?
No. So geodesic is actually, we approximate that. So basically you have a V and then you integrate that. So actually you can see that the square root of that infimum, like a minimum geodesic will be upper bound of this mean square that we have shown you before. So I don't have that visuals here, so they are clearly related. So related, what I mean by that is that you actually compute this error bound. I have to go back to the contraction theory. So you have your error bound is mean squared error, but then you can compute how that's related to the square root of the shortest path integral, which is actually minimizing geodesic.
Yeah.
Yeah.
You don't have to.
You don't have to compute that because I mean, actually in our stochastic version, we are using that as an analog of our mean squared error distance, but eventually what you care about is actually mean squared error. But they are upper bounded or lower bounded by each other, so they are related. But you don't have to compute. But you can get to the upper bound here.
Very online. Anybody else? I think everyone wants to go to snack. So
How do you find that the ranges like high control kind of thing that you separated out the base condition? Like the main parameters, also like you paid the last year doing the network. How was that found? Only that is it?
So maybe I don't know if I understand your question, but maybe it's a complicated question. So you're talking about non-affine control input?
Yeah, basically separate out the U and multiply it with them. Same thing like you wrote the main parameters like multiplied with something.
So that was the general model. I think in Eurofly, we actually assumed that your disturbance is not function of U. But maybe you can be trained as a function of U. But I can tell you that in the neural lander, it's actually a function of U. So what you do is that we can use the previous value of U, because otherwise you have to solve this implicit function where you don't know U. So you actually take the previous value of U, and but still like it's similar to contraction theory. Over time, using some contraction mapping, we actually show that it's actually kind of converge. That's what we show. Yeah. Right.